Okay, and you may begin.
Okay, well, thank you for having me. It's always nice to speak. So today I am going to talk to you about my own research, which fundamentally is looking at the connection between star formation and galaxies. So just a bit of context and motivation. So all of this research takes part in the interstellar medium. So basically, the interstellar medium is all the gas and dust that you have in the galaxy between the stars, essentially. And basically, see when you see all the lovely, pretty Hubble images, this is usually images of the interstellar medium. We see these spectacular nebulae, all glowing in the different colors. So, for example, I've put the Vela supernova remnant here on the left of the screen. And you can see all these different phases lit up. This is looking at the interstellar medium. And basically, you can break it up into different components, which is what I've put here on the right. So the densest parts of the interstellum are the molecular clouds made up of molecular hydrogen. And this is where you get your stars forming, just like our sun and our solar system and the clusters of stars. These all form in the molecular clouds. And then these are surrounded by a neutral hydrogen, number densities of about 30 to 100. And then you surround that with warm and ionized hydrogen, all the way up to hot phases. And so you have these kind of blobs or clouds of cold, dense gas surrounded by warm hydrogen and hot ionized hydrogen. And this is all fed and energy is injected from surrounding regions of photoionization, from young hot stars, that will be stars, and also, of course, from energy injected by supernova. So this stirs up the material in your gas, it keeps things moving. And on the larger scale, you also have the large scale galaxy motions, which sweeps this gas together. And so this gives you this gas cycle, which takes place throughout the galaxy. So if we look at specifically where we are, so I've just put up a little map here. This yellow dot is the sun. And you can see around us, we have different spiral arm features. So above this yellow dot, we have the Perseus arm. We are just a little spur off the end of the Sagittarius arm. And surrounding us, we have this thing called the Gould belt, which is all the local molecular clouds which we see. They lie within this region. And what you can see is that there is this connection between the structure of the galaxy and, of course, where the gas of the galaxy is. And that has implication for the stars, as I will show. But before I go on, there's one thing I did want to show because I think it's really cool. For a long time, we've had this thing called the Gould belt, and we thought all the local molecular clouds, the regions, the stellar nurseries, formed this sort of belt. So if you think of your classic nearby star forming regions, for Orion being the major one, but Perseus, Rho Fucus, all these nearby clouds, which is where we build up our understanding of how stars form, because this is the place where we've been able to observe with the highest resolution, because of course it's closest. But with the advent of new instruments, and specifically Gaia, what a collaborator of mine, Catherine Zucker, has been able to do is to build up a 3D map of the Milky Way, and certainly the nearby galaxy and the nearby stars. And that's because she's been able to use the exact positions of the stars to work out the extinction, so how reddened the light from the star is by the intervening dust, meaning you get a 3D estimation of the local gas density. And so for the first time, just within the last year or so, instead of when you look at how stars form in galaxies, instead of it just being a 2D picture, you're actually beginning to see a 3D model. And Catherine and her collaborators have applied this to our nearby star forming regions. And what they found was that this thing, which we always thought was a belt, is actually a wave. And all these famous nearby star forming regions are actually associated with the wave. And so if you look up here in the top right, you can see this sort of almost like a sine wave. And there's this extent, the material's been kicked out of the disk and it's coming down again, down the bottom. And it's this kind of string and everything's connected. So for example, here you've got Orion close to us, but you've also got the North America nebula, Cygnus, all these different regions, you can see them here. And so all these nearby star formations are actually connected, and they seem to be connected to the larger galactic structure. And so I've just got some pretty nice images here. So we've got Orion, this is Orion A, the famous region where the most massive star formation is happening in the Orion Nebula. And on the right, we have Ophiuchus, which is a nearby lower density region of star formation. So I've just explored how there is this connectedness between the regions of star formation on a galaxy scale. But I think if you look into this, you can see, well, there's structure within the cloud as well. So here's a little movie from some of my previous work in 2016. And this shows you one of my simulations of the evolution of the molecular clouds. And you can see how the gas moves within the region. There's, again, just so you can see, so there's large scale shear, which stretches the gas. You can see there's small scale structure. And there's this one central filament which arises through the center. And there's little points along here. This is where the stars form, just like beads on a string. And so this filamentary geometry is something which we see again and again in these molecular clouds. And the filaments are formed due to a combination of the gravity, pulling things together, making things collapse into sheets, then into filaments, but also due to internal turbulence, supersonic turbulence, which drives velocity fronts through the cloud, which become dense and sweeps gas together, where it can become gravitationally unstable. And so we have this hierarchy of structure, which is driven on the largest scale from the parent galaxy. So I've put on the left here the M51 Whirlpool Galaxy, and you can see these beautiful spiral arms, these dense dust ridges, which are clearly associated with the spiral arm. And along them, you can see these red points. These are embedded regions of star formation, reddened by passage through the dust. And you can see the association. But the challenge for an astrophysicist is the different scales which these arise on. This image on the left here is 18 kiloparsecs. The image of Orion, which I just showed you, the very pretty one, if I put that on the same units, that's 0.0037 kiloparsecs. And that's the entire cloud. The actual stars form in scales of 0.1 parsec or smaller. And so you have the large scale galaxy forces which are shaping these regions, which are gathering the gas together, which are driving the top level of the turbulence, which will then cascade down the energy cells. But then within the galaxy, within that molecular cloud, you have the stars. And what do stars do? They ionize their surroundings. They inject energy and material back into the interstellar medium. They create supernova, which then drive this turbulence, which then affects the mass flow, which then goes back up to the larger scale. And so the evolution of the galaxy proceeds. It's intrinsically tied to the star formation within it, but these happen in very different scales. And so that's basically the fundamental issue, which I'm looking at my own research, is how do we connect these two scales? And the filamentary nature of the interstellar medium just really shows how connected these regions are. So this is from a recent review, which I've been involved in. And you can see in the middle, you've got your lovely view of the Milky Way, you've got the galactic plane there. And we've just highlighted different structures within it. So we have these H1 filaments up here, these almost like striations of very diffuse atomic hydrogen, which have a filamentary geometry. Then we have a nearby molecular cloud, which has a filamentary geometry. Inside it, you have these things which we call striations, which have a filamentary geometry. If you go even smaller within these striations, you'll find that there are subfilaments or fibers within them. So at this point, if you're taking a drink for every time I say the word filaments in this talk, you will end up very, very pissed, okay? So I would highly suggest you do not do that. But there is this recurring theme. And it's connected to star formation and to the galaxy structure. So I'll put here, there's a little point for a hub, and you can see these filaments running together into a central point. And where these filaments overlap seems to be involved with massive star formation. A bit more about that in a second. So just to reinforce this point even further, this is the Nessie filament, which as a Scot, I am contractually obliged to talk about in every talk that I do. And you can see it's very, very long structure. It's 100 parsecs long. And it seems to be that you're looking at something that is lying right in the center of the spiral arm where that dense gas has been connected. And then we see even longer structures. So we're also now in the H1 gas, this atomic hydrogen, see these really, really strong structures. This is a filament in H1, which we've just discovered with the Thor collaboration. And it's 1 kiloparsec long. It's like 5% of the galaxy, this H1 structure. And it's there and we never knew about it before. And as I just said, within the individual clouds, you see it again. This is Taurus. And so you can see there's these fibers I was talking about earlier. You can see these small structures which you identify in the gas. And so these thread the entire galaxy. And this is a plot where we've discovered every single filament in the entire galaxy and collated their properties. This is just about to be published as a part of this huge big review that we've done, this meta-analysis. And you can see there's this hierarchy that all these different structures, they tend to live in this fundamental plane with regard to their mass versus their length, right up until the Tumri length. So that's the scale of gravitational instabilities in the large scale galactic disk. Right up to that level, you're seeing these structures, and they're nested within each other. It's fractal-like, it's levels of structures within structures, which seem to all have fragmented. And then we can look at how the velocities of these objects change. We find that the smallest ones are sonic, but then as they get larger, they get increasingly supersonic. And so altogether, this has led to a picture of the interstellar medium, which cares about the local geometry. It matters about the large scale. And this complex network of structure, which connects the largest scales to the smallest scale, and then influences how the stars form. So on the left of this image here, I've got a plot by Kunkel et al. In 2019, and they've looked at these Gaia data. And what they identified were strings in the stars. It's like the stars which they find in Gaia seem to be connected to each other. And one theory for this is this the legacy of this formation in these filamentary networks which kind of thread the galaxy. So the question you might ask is, does this matter in terms of how stars form? And I would answer, the correct answer is probably yes. And there are two reasons for that. First of all, because it sets the most likely mass of a star. If you look at a perfect isothermal filament, if you think about the growth of an instability, there is a characteristic instability which will collapse the fastest and will win, essentially. And that would be determined chiefly by the width of the filament. So about the fastest instability will be about 2 times the width of the filament. That's the perturbation that will grow the quickest. And if you look at the typical density of one of these filaments, which we find, you find a peak roughly around 1 solar mass. And that indeed is where we see the peak of the initial mass function of stars. That's the most likely mass. But this distribution also influences how you might form the most massive stars. And these are the massive stars, the ones which are so crucial for the galaxy evolution, because they're the source of the feedback from photoionizing photons and also from supernova. So this is some work I did in 2016, and it shows you from one of my simulations different networks of filaments. The crosses show you where the stars form. The crucial point is the arrows which show you the velocities. And you can see that this sort of channels mass down towards the, there we go. Oh, give me a pen. Thank you. Channels mass towards where the stars are forming. And this means that that star, that point where you have a point of fragmentation, where you have something which is collapsing, which is accreting gas from its surroundings, it can become even more massive because of this collapse process, feeding a constant reservoir of mass towards the forming protostars to enable that star to grow more massive beyond that point, that most likely mass of a single instability in a filament, and allowing you to build up the high mass end of the stellar initial mass function. And so this filamentary network, which you form through the assembly of the clouds, through galactic scale forces, and by supernova feedback injecting turbulence, directly determines the type of stars which you form at the end. And so the question always is, how do we test this? How do we investigate this? Well, one good way to do it is in simulations. As we know in astronomy, it's quite difficult to do experiments. And so one of the ways you can get around that is doing numerical experiments, where you build your model, you put in the physics that you think you need, you run the simulation, and then you see how similar the outputs you get from that simulation are to reality. And that tells you whether your theoretical understanding of the process is sound or if there's something you're missing. And so my particular suite of simulations has the kind of tagline Cloud Factory. That's mainly because I didn't want it to sound too, to give an impression of what it is. This is a machine for making clouds. It's not an absolutely perfect galaxy simulation. What it's aiming to do is calculate and capture the properties of the interstellar medium in a galaxy. And so we have all sorts of ingredients. We have a chemical model, which is really necessary to follow the different phases of the interstellar medium and find out where you have the molecular gas for the molecular clouds. We have heating from the interstellar radiation field. Obviously, we model the galactic potential and the gravity. And we use an approach called sync particles to model regions of star formation. Basically, where we have a blob of gas, which is unambiguously collapsing. So the potential far exceeds the kinetic and thermal energy of the gas, and where the collapse is accelerating inwards, we replace it in our simulation with one of these sync particles. Regions either represents either a single star or more typically a small stellar cluster. And that allows the simulation to proceed beyond the point where your first object tries to collapse to a star. So you don't have to go all the way down to stellar densities. And in some of our simulations, we also have magnetic fields. Okay, so this is what the simulations look like. I've got different flavors here, depending on how I do my feedback from supernova. So in this one, the bottom one is clustered feedback, in the top one it isn't. So in the top models, the spiral arms dominate more, and in the bottom one, the feedback from kind of massive cluster supernova feedback regions dominate. And so we have this very large region. It's more than 20 kiloparsecs across, but we focus our resolution in a box which co-rotates with the galaxy. And from within this region, we can select individual clouds, which we then resimulate at really, really high resolution. So we capture those galaxy forces, but we can look at how that's impacted on the structures formed within. And so here are 4 of the different regions, 4 different cloud complexes, which we've done at really high resolution. So we go down to about 0.1 parsec at the regions of the kind of densities of the filaments of these regions, which is pretty good for a galaxy simulation. And so we can look at how the different clouds look and see whether the different galactic environments in which these 4 clouds were formed has influenced the star formation within them. And so you can see some quite different regions. So the top one, complex A, that's something which is formed in the middle of a star formation, a spiral arm, where we don't have clustered feedback. And the bottom one is something where there's been a lot of dense cluster supernova feedback. And we can see the properties are really different. So on the top one, we have these filaments, which are much longer, they're much more continuous. On the bottom at once, you can see that the filaments within the cloud are far shorter. The other thing we can see is the coherency. If we look at the velocities within these different environments, we can see that the longest filaments, the blue and the yellow ones here, which come from the region without the cluster feedback, the potential dominated regions, the velocity gradient along the filament is much lower. So when you have these long structures, they have a very low velocity gradient. They're very coherent objects. They will travel together. Whereas the very short ones, they have a lot more higher shear. So they would be rapidly torn apart. And the other thing we see is a difference in the star formation. So for any filament, there is this critical ratio of mass to length, above which the filament will collapse and is susceptible to fragmentation. And that's everything above this grey line in this figure on the left. And so what you can see is that in the region which was associated with the spiral arm and this more less supernova influenced dynamics, all the different regions of the cloud reach that threshold almost simultaneously. And so you get these very rapid episodes of fragmentation, which leads to these almost like clusters following around here. So you can see a big cluster forming here. And what's happened is there's been a rapid epoch of fragmentation. This is all collapsed and it's rapidly built up a cluster along this front. And it all happens in a very short time scale, like a couple of meg years. Whereas for the environment where you've had greater stirring from supernova feedback beforehand, you find a much more distributed and sequential star formation. So in that case, we have plenty of filaments which are below this threshold for fragmentation, and they just gradually over time evolve above the threshold. And so as a result of this, you get little mini subclusters within the region reaching that threshold for instability, forming stars, but it's happening in a more gradual fashion throughout the cloud as a whole. And so we can see that there is an impact on the local galactic environment and the history upon how the stars form. So how do we compare this to observations? So just a couple of examples here. So this is some images from the dwarf survey, which is a survey of the Milky Way looking at each one. And one of the things they've done here is they've processed the image to bring out where the filamentary structure is. So that's these top two panels. On the bottom, we've done the same thing to the cloud factory, which of course is a bit of an extreme version. But the point that is important is that what we find in the cloud factory is that the only way we get vertical filaments in each one is when we have strong clustered feedback. And when we compare this to the Thor survey, what we find for the most part is that the filaments lie parallel to the galactic plane. Every so often you get the vertical ones. So what we think from the simulations is that might be an indication that is a region where there's been recent strong supernova feedback. Another way we can do it is a machine vision or machine learning technique. More machine vision is a way to kind of automatically compare two images to see how similar they are. And if they're similar in this plot of the histogram of oriented gradients is what we call a technique, you get a straight vertical line, diagonal line across the gas. And so one of the things we can do is use this to compare the emission, which you would see from 13CO, so a molecular gas tracer, with the atomic hydrogen, to see how closely those different phases of the interstellar medium, which I talked about in the introduction, to see how closely they are associated with each other. And what we find in the survey is, for the most part, they absolutely line up. But where we see differences, every so often you will see an offset. And again, we wonder whether this might be an indication of feedback. So we can't test that in the observations because we can't run back time, but we can test it in the simulations because we know where all the supernova are. And so what we're working on at the moment is comparing the signature of how closely the different phases are of the ISM and where we have feedback and where we don't. Another thing we can do is, using our radiative transfer of the simulations, we can make synthetic emission maps, 13CO, and we can try and identify some of these structures, which I told you about in the introduction, these filaments, these clumps of gas. And we can try and identify the exact same thing in the simulations, which we're doing here. And as you can see, we're plotting the same properties that we have for the observations for the mass versus the length. And that's a way to test whether you can explain these features with large scale dynamics and gravity, or whether there's something missing in our understanding or in these models. And also by turning different physical processes on in the simulations, you can try and work out what is the most important process, try and work out the partition and to see what is, really important physics and what is just a second order effect. And so by doing that, you get these lovely images. I'm quite chuffed with this one. That shows you a region of star formation. And this is entirely simulated. This is just from one of the simulations which has been transformed into the observational plane. And you can see within it, for example, here, we can identify the smallest level of the filamentary structure. And that's what's allowing us to critically test against our observations. Okay, so in the first part of the talk, I concentrated on local environment, looking at the Milky Way. But just to come to a finish, I thought it might be interesting to extend beyond the Milky Way and look at star formation in other galactic environments. And so one of the things I showed you earliest in the introduction was M51, which is this very nice grand design spiral galaxy. And so with a student I work with, who's actually just passed his PhD, Robin Tress, he's built a model of M51, and you can see it's very beautiful, very pretty. And one of the questions he was interested in is that we know that M51 has that strong spiral pattern because there's been a close encounter with another satellite galaxy, and that's what's driven these large spiral arms. So the question Robin asked was, what if that encounter had never happened? Would the same number of stars have formed anyway? Or is there something about that close encounter which has enhanced the star formation? And of course, he and I and most of the people in our team confidently said that it had enhanced the star formation. And as it turns out, it's done absolutely nothing. So when we look at the model where we have a flyby of a perturber, and when we don't, you look at the star formation history, that's the orange versus the blue, you can see the star formation history is actually very similar in both cases. So what the encounter has done actually is just change where in the galaxy those stars were formed. But using this model, we have been able to build a complete census of where the molecular clouds would be in this fake galaxy. So you can see them here where they've been pulled out using our dendrogram algorithm. As you can see, they are filaments, not blobs. But so we have this complete census of the clouds in the galaxy. And again, we can think, okay, what do we learn about star formation and comparison to observation? So we just looked at the distribution of different of these things. And our hypothesis was that within a disk, you might find larger clouds in the spiral arms, for example. And again, this was absolutely completely untrue, which was a bit surprising. What we found was that the masses and the size of the clouds, it didn't really matter where in the disk were. What the difference between the spiral arm and the interarm region was that you got more clouds there. They hadn't actually changed their size distribution, with one exception. And that exception was the galactic center in this model. And here, that's the yellow line. You found much more massive clouds. And that's interesting because that's something we also see in the Milky Way. In the galactic center of the Milky Way, you get statistically far larger, far dense clouds with higher turbulence. But something this catalogue allowed us to see was look at what level in the hierarchy of structure does the gas become bound. Because one of the things about star formation in galaxies is it is a very inefficient process. We find that you're looking at percent or less, far less, 4 solar masses per year of masses converted into stars in the Milky Way, which when you're looking at a gas mass of 1 billion, is really, really inefficient. And previously, people would have thought about forces like the magnetic fields, maybe, or turbulence, think, how do we support the galaxy against collapse? But actually, what we have, not just my own group, but as a community have seen for the last 10 years or so, is that these clouds, these associations of molecular gas are actually gravitationally unbound. And so what Robin did was he looked at different levels in the hierarchy of structure, from down to the smaller scales, to find where things become bound. And that's what these plots here are. You can see there's lots of different variations. So anything that's in this grey region is gravitationally bound, it's above it. And as you get to higher densities and smaller scales, you start from being completely gravitationally unbound, just an association, down to the smallest scales, where you actually do become bound and collapsing. And so what we see is that in these cloud complexes, only tiny little bits of them will actually be collapsing and star forming. And that does explain why star formation is slow in galaxies. So the final thing I'm just going to talk about is just going even further back to look at kind of low metallicity dwarf galaxies, such as you might find back in the early universe. Is something I'm doing with my PhD student, David Whitworth. So this is a very pretty image. Yeah, we're astronomers because the images are pretty. And it shows a low metallicity dwarf galaxy, which David has simulated at different metallicities. And we've been able to look at where the molecules form within the glass. And what we find is, depending on the metallicity, so that's the ratio of carbon and oxygen in this case, you get different amounts, and dust, critically. Dust is important. And you get different amounts of molecular hydrogen formed. And so molecular hydrogen is the blue, and you can see that there are different amounts of it in the different regions. And also you can see that changing the chemical composition of the gas has had a big impact on the galactic structure. So the lower metallicity case is much more compact. It's a smaller galaxy. So it is fun to see how just something as small as the chemical composition of the gas can completely change how the galaxy appears, because it changes the thermal energy balance, because it changes how efficiently the gas can cool. But the interesting thing is, despite that difference in the molecular gas content and the geometry of the galaxy, how tightly the gas is confined, the star formation history is actually very similar. So this is the red and the blue lines are factor 10 reduction in metallicity and interstellar heating. And what we find is that despite this factor 10 reduction, the star formation rate is almost identical. And this is showing you that what's really important for the star formation is just where the cold, dense gas is. It doesn't really care about the molecules of H2. But something we have found, which is pretty cool, is when we've run some magnetized versions of these simulations, this is work we're doing at the moment, we have found that does make a big difference to the star formation. And normally you think when you have a magnetic field, that would slow down star formation because it supports the gas and makes it harder for the gas to collapse. But what we found is, in the early times of the galaxy, where the field is still weak, so it hasn't been amplified by rotation up into a saturated level as you would see today, when you have this weak field, it actually enhances star formation. And that's because the magnetic field lines threading the galaxy make it harder to blow material out of the dwarf galaxy due to supernova feedback. And so we found that there was almost a factor of 10 increase in the star formation rate of these galaxies when you include a weak magnetic field, such as you might expect at a dwarf galaxy formed early in the universe. And of course, that has implications for how the galaxy evolves, how mergers might proceed, and the enrichment of the galaxy, because every generation of star formation will then inject metals into the ISM. And so that has some quite interesting implications, I think, for our understanding of how these dwarf galaxy systems evolve. And we'll just stop that. And so this is my summary. There's time for questions. So we've used a customized version of the repo code to model the dense ISM on galactic scales. We have found that galactic environment feedback alters the filamentary structure of clouds, which alters how star clusters are assembled in different environments. And we've included time-dependent chemistry, and we've used radiative transfer to allow tests with observations. And in two different examples, which are extragalactic, so we found like an M51-like model, the cloud sizes were not affected by the spiral arms, but were increased in the galactic center. And we found that only the smallest scale structures in that hierarchy of structure were gravitationally bound. And we also showed that in low dwarf galaxies, the star-dependent formation was independent of the molecular content, but at the moment does seem to care about a weak seed field. And with that, I shall stop. Thank you very much.
Thank you for giving the talk. Now we'll open the space for questions. If any questions, do raise your hand. Give you the spot. You can also ask in the chat if you like. Claudia has a question. You may proceed.
Hi, yes, thank you for the talk. I was curious about the sort of these filamentary structures and how they link to the formation and to the structure of the galaxy and everything. When you said of the magnetic fields and how they are enhanced in weak fields, then can we assume that these sort of structures are default or intrinsic to galaxies? So could we assume that any isolated galaxy will evolve to be this type of galaxy with spiral arms and this type of formation?
Yeah, so the spiral arms, that's a very large scale instability. So, you know, it's an emergent feature. So you can either have the grand design spiral arm, which often is caused by a perturbation on a larger scale, or the kind of flocculent galaxy distribution, where you'll get reinforcement from the stellar distribution, which will drive these large scale spiral waves. The filamentary structure within it, that seems to be something which you would find in all galactic environments. When we look at where the filaments are coming from within the galaxy, actually the trouble is that there are so many different ways of getting them that sometimes we find it hard to actually separate out the precise physical mechanism. So you mentioned magnetic fields. They create filamentary structures because of course they have a preferred geometry, and that means gas is more likely to flow along the field line and it's harder to compress in the other directions. However, gravity also gives you filaments because of the way gravitational collapse proceeds in a finite medium. So you first of all collapse down into a sheet, then you collapse into a filament, and then into a point when it's finite. And that's why if you look at these cosmological simulations, you know that you have this web connecting all the galaxy halos. That's pure gravitational collapse, which is causing those filaments. But at the same time, you get turbulence where you have shocks, you know, hydrodynamic shocks on their own gives you moving velocity fronts, and that gives you these filaments. So that filamentary structure must be a general property of the interstellar medium because you have so many different mechanisms to create it, and therefore it should be a general property of galaxies.
Yeah, makes sense. I also have another question if people are okay with me continuing. Also, after when the galaxy evolves, sort of, is there a point that this filament and this formation just stops or dies off when?
Not while you have gas reservoir. So if you think about it, you have to be, if you have a kind of large scale driving, I think you would do that. So if you have material which is irregular and collapsing, then you should still have this filamentary network. It would be slightly different if you're in a very evolved galaxy where you don't have much gas reservoir left. That's always going to be less pronounced just because there's less gas. And also if you had a very low rate of supernova feedback, that would also change how the energy was deposited into the ISM and how that drives those structures. So if you look at the two models I showed where we had the clustered feedback and the one where it was more distributed, if you think of a galaxy where the star formation rate was incredibly low, you would have a much smoother distribution. And so you wouldn't get these really short filaments so much, it'd be larger and smoother, at least on a large scale. But it's hard to think of a point where it'd be entirely absent.
Thank you.
Does anyone else want to ask any more questions?
Yeah, so with the M51 galaxy, where you were sort of simulating the perturbation from a flyby of a dwarf galaxy, what sort of initial conditions do you use for the M51 itself? Or is like some sort of galactic potential, or do we know how to model that?
Yeah, so it's an isolated galaxy which we've allowed to relax. So we have a dark matter component, we have a stellar bulge component, and then we have the gas. So we model the dark matter halo, we model the hydrodynamics from the baryonic matter, and then we have this stellar component. And the properties were chosen of those different components were chosen to be similar to M51. There are a slight difference in some of the properties. It's a little bit less massive, just because it's hard to get an exact match, and we needed to get something that was stable, given those components and the fact that we are just measuring the galaxy on its own. But yeah, it's a multi-component matter. We model the dark matter, the stellar stars, and the gas in an isolated galaxy, this galaxy.
Makes sense. Thank you.
All right. So next question.
I do have another question, if that's okay.
Yeah, of course.
It's about sort of two things you said, just linking them together when you were showing that similarity between the structure for hydrogen and then for CO. And then you're also talking about metallicity at the end. Do we link those similarities in structure between the different molecules together to estimate like starting conditions of stars, for example, like their metallicity or their composition?
So in terms of, I mean, there's slightly different scales. So we know that the stars form from the molecular cloud. So in terms of the composition of the star, then that has to tell you about the metallicity of the star. That's the gas it forms from. But obviously the star then will evolve and then feed back into its surroundings. So in terms of the individual properties of the star, but I'm also interested in the properties of the population of stars. And I think that has to be influenced by the properties of the cloud in which it's formed. So if you look at how much of the star, of the mass of the cloud is converted into stars, that has to be linked to how gravitationally bound the cloud was to start, the level of turbulence, which kind of supports and fragments the cloud into different regions. And these properties are set on the larger scale. So to answer your question, the properties of cloud have got to influence the statistics of the cloud, the stars that form within. And obviously that is the mass reservoir which the stars form. So the star will inherit the metallicity of the cloud it's formed from.
Yeah, thank you.
Are there any more questions? All right, if there are no more questions. Then thank you, Dr. Ron Smith, for agreeing to do this for ultrasound. And I hope everyone has a great day. And I will end this here now. Thank you.